I'm in the middle of the blue sheet. I think it's on the back, in the middle-ish section. Advanced integration techniques. It's here I'm at. Okay, here we go. Okay, it is required, expected as a Calc 2 topic that you can do partial fraction decomposition. However, only the easiest ones are on the AP test, the ones where you're non-repeated linear factors. Now, that said, what does that mean in plain old English? This one you would have to be able to do. This is a repeated factor. You would not have to do it, although you should know that you do 1 over x plus 2 plus another 1 over x plus 2 squared, right? College, they would expect you to be able to do that. And this is the ax plus b1. When you have an irreducible quadratic, which is to say a quadratic that can't be factored over reals, then you would use the ax plus b method here. Maybe in the interest of time, let's just say not AP, but you would do it as ax plus b over x squared plus 1 plus c over x minus 4, and you do your process, right? This would be a over x plus 2, b over x plus 2 quantity squared, c over x plus 3, but this is not on the AP test. Okay? Making arctangent or arcsine, I don't know how necessary this is because we did this before you learned trig stuff, so many of you wouldn't try and adapt this to make 1 over 1 plus u squared, so you could do arctangent. Many of you would just say, you know what, I'm going to trig stuff and go, and that's fine too. Either way, though, I've rarely to never seen anything on the AP test this complicated. It's more of garden variety. Do you have a basic clue? Maybe a U sub with maybe something like this. I think is as ugly as you would see. 4x to the. Let's go here. What if this was 4x squared? What's the process? U sub. What if this is 4x to the 4? That's either trig sub or call it arctangent kind of thing with u sub. You would call it 1 plus 2x quantity squared, and maybe u sub it to make it arctangent-ish, right? Okay. Completing the square is also not an AP question. That's a college level question, but not an AP. If you are to do that, just to get you really started quickly, the technique is that because it doesn't integrate well, it doesn't factor well, and partial fractions wouldn't happen, you would probably complete the square. You would say, if I put something there to complete the square, what completes the square?
4.
A 4. You'd subtract 4 to balance. Then it becomes 2, and x plus 2 squared plus 3, and then you could do your trig sub or arctangent kind of work. You with me? All right. I don't want you to be at disadvantage next year just because there's on the AP test doesn't mean your Calc 1 colleagues that took it in college level wouldn't know it. Improper integrals. Improper integrals, there's 2 types of improper integral. One is where it slaps you in the face, obvious. If you see infinite there, well, that's an unbounded region. That's obviously an improper integral. The more subtle is where you get a lack of continuity. This has not so much a horizontal asymptote, but a vertical asymptote at 1, and you would have to be careful. Limits and all that stuff. I got to say, if you did this, like something like, if you did this, there's something like negative 1 over 2 minus x to the negative 1. I think there would actually be another negative. If you did this, and it was on a multiple choice, I wouldn't know. I think I would actually be in my room while you're taking the test, and I'd feel a chill all of a sudden because somebody just broke calculus. But on a free response, that's absolutely unacceptable. You cannot do that. You must use this. Okay? All right. My point, though, is if you need to understand that there's a mix of Calc 1 and Calc 2. You need to check continuity and say, is this a normal Calc 1 kind of question or an ugly Calc 2 kind of discontinuity question, right? Right. Okay, trig sub. You'll be happy to know that trig sub is not on the AP test. Yes. It is, however, a crucial technique. It's super important. These notes are just by way of for review for you next year if you take these to college. Just to remind you of the trig sub facts, okay? Numerical integration methods. There are 3 ways. Actually, I shouldn't say that. There are many ways to estimate an inverse. Give me one. Rectangles. What is the subset of rectangles? Left, right, midpoint, left, right, midpoint. Technically lower and upper, but that's not an AP test. All right, so rectangles, also known as Riemann sums. What else? Actually, pause back there. Rectangles. Overestimate or underestimate based on not concavity. Increasing or decreasing. Okay, it's all about increasing or decreasing. Okay. Trapezoids, you say. Trapezoids, you have equal and unequal. I'll get to that. But that's based on concavity. There's also Simpson's rule. That is not on the AP test. You do not have to. Okay? All right. Rectangles are the starting point of the fundamental theorem. So let's remind you of the development of the fundamental theorem of calculus. It's kind of important. Are you ready? Okay, it goes like this. Would you consider some kind of curve from 0 to 5? Now, if you were to break this up into, let's say we use right rectangles, then you would have to be told how many right rectangles. But the idea is that the area under the curve is many base times heights. The base is always a delta x, and the height is the function at some x. So it might be at the first x, and a delta x for the base times the height at the second x, and so on, right? Now, specifically, delta x is found by taking the region and dividing by how many? So in that case, what's delta x? 5 over n. Now because it's a common base, it's equal subdivisions, we can factor that out. The first height is f at, now if I use right rectangles, then I started at 0, went over a 5 over n, so the first height would be f at 5 over n. The next height would be f at 2 5 over n, until I ended at the either the nth 5 over n, which simplifies to 5, or f at 5, right? You will sometimes see this in the oh-so-scary summation notation. Now that you're Calc 2 students, summation notation don't mean nothing to you. You covered it later, okay? That said, it is the idea that you take an infinite number of rectangles and rather than write all those f's added separately, you say it's f at some multiple of 5 over n, where I is the counter. So you got two things going on. I is the counter of what rectangle or what division you're at, and n is how many rectangles you decided to use. You with me? Now, that said then, as the number of rectangles goes to infinity, then that sum becomes more of a theoretical exercise, and you use a Roman S to show it. That's where the definite integral comes from. It's actually an S. The 5 over n, if I take the number of rectangles to infinity, then those rectangles get thinner and thinner. As n goes to infinity, 5 over n goes to 0, but really more like that delta x goes to 3. Okay? Now height is f at different functions. And so you're really summing, although the integral is so many other things to us, at its heart, it's the sum of many based on heights. And limits of integration just signify the region. Okay, now that said, things get rougher when you start somewhere besides 0. If you started at 2 and went to 5 and did rectangles, then you'll see that 2 in your work. It's still based on height many times, and it's still delta x times lots of function values. But here's the deal. First of all, what's the delta x now? 3 over n. The true showing up of that 2. Now that 3 over n, that's a little loaded, because that just shows the width is 3. It doesn't say where it's 3. Is it 0 to 3? Is it 2 to 5? Is it 1 to 4? 3 wide could be a million different places, right? To see where it started, you actually have to look inside where the functions are. The first x at which you drew a height was not just 3 over n, because you didn't start at 0. You started at 2 and went up 3 over n. So the first x at which you drew is 2 plus a 3 over n. The second x at which you drew was 2 plus 2 3 over n's. So the x's at which you draw are always 2 plus some number of 3 over n's. Right? So if you were to write this in summation notation, the limit as n goes to infinity of the sum of this. Now, the delta x is still 3 over n. F at n. If you see something besides a 3 over n or a delta in here, if you see something added here, this shows the starting value is something other than 0 in this case too. So that combined with the width can tell you the limits of integration are 2 to 5 of the function. All right, now then, it's common and always a gotcha for problems that you'll see the question asks you, multiple choice question, I've asked you to go back and forth between these two forms, an integral or a Riemann sum summation. So if you look at this and say, what definite integral is this equivalent to, then this guy tells you the region is 3 wide, but this guy tells you it starts at 2. So it goes from 2, 3 wide to 5. The inside function, then the function tells you this is the dx, okay? So this must be the function. Now the 2 is the starting value, so what's the function? X to the 5th. Now, a very logical question and a great one is, maybe you can think of it. What else could that's actually could be one other thing. What else could it be? Could be 2 dx to the 5th. Yeah, the function could be 2 plus x to the 5th. In other words, that 2 could be part of the function, and the values would be from 0 to 3. Well, how can that possibly be both of those? Well, think about it graphically. If I did x to the 5th, it's like an extreme x cubed, and it would be this region, yeah? What does that do to the graph? Shift it left, right, up, or down? Left 2. And from 0 to 3 would be exactly the same. Okay? Now, they would never have a question where they had both choices, but you do need to be aware that it is 2 possibilities. They don't get that gotcha-ish. I would, it's always this. I mean, they don't get 2. Okay? So, with that said, would you give me, actually start with this one, it's more straightforward. Would you do the second one as an integral? We'll probably just do 2 of these. Would you do that as a definite integral, please? Go. Did that sheet make its way around? Oh, it's here. I got it. Thank you. Oops, I'm good. Okay, so ready? Limits of integration. 0 to 4, function. Okay, good. All right, try this one. There is no I in the, oh, there should have been an I. Sorry, my bad. My bad. Should have been an I. It would have been in the, here. Sorry about that. Good eyes. Okay, ready? This could be part of the function, but it could also be the starting value. So let's assume it's starting value. Starting value is 1. The width of the region is putting you an n value of, and the function is? All right. What about this? Sometimes you see an expanded form, not a summation form. Could you do that one, please? Okay, so what's the region? 0 to 2. What's the function? 3. Okay, let's go the other way. Sometimes you're asked to match an integral to a summation. I didn't give you enough room to do this one, so let's go to this one. First of all, the only way you get a definite integral is if you have an infinite limit of the sum. It's infinitely many rectangles, so it needs to be there. I'm not picky about the indices. It really goes to whether you're using left or right. So that's why I don't usually put them. But let's go from I equal 1 to n is the most typical. That's right. Left is 0 to n minus 1. That said, what's the delta x? 4 over n. And what is the function cubing, and what's inside the function? 4I over n or 4 over n, right? And that, all that quantity cube. Okay, we good? Try the next one only, and then we'll be good. Something. So everyone should have the basic formula is a delta x and an f at x kind of thing. So the delta x is 3 over n, yes? And the function is 2 over root something. What's in the something? 1 plus 3 over n I times. Okay? All right. Trapezoids. There are 2 different types of trapezoids. You can expect both. One is if equal subdivisions are used. If equal subdivisions are used, then you can factor out the delta x over 2. And inside is that 1 on the outsides, 2 on the insides pattern that we've seen so many times. Do you remember? Okay. If unequal subdivisions are used, which is usually a table problem, free response, though not always. If, for example, you went from 0 to 2, then from 2 to 7, and then 7 to 8, you can see that these delta x's are all different. Now, if they're all different, then obviously it's not common. If it's not common, you can't factor out a common factor. So it is then more of a piece-by-piece kind of deal. And last but not least, if it's free response, remember, underline. If it says use trapezoids to estimate or approximate, would you please pause and say estimate or approximate? While I'm thinking about it also, if it says round, underline that and round. Be careful if it says to round in part B, but they don't say anything in part C. It's a really easy rule. If it says round, you should round. And if it doesn't say round, do not round. And don't assume that just because in A you rounded, that in B and C you're going to round. That is not the case. It's very common that people just crank out rounding. You lose. Okay, so round when it says to round. If it says round, then underline that as well, okay? Okay, I think that is good. Yay, here we go. Let's go yeller, shall we? Fundamentals, theorem of calculus. Yeah. Oh, sorry. Calculator error bound is, did I put that on you?
Yeah.
Oh, sorry, it's not on the test. Okay.
Can we still know?
Simpsons rule is also not on the test. Yes, if you'd like to put that in your notes, trapezoid error bound is something like, not something like, is error is less than or equal to b minus a cubed m over 12n squared, where m is the max or upper bound of the absolute value of the second derivative on the interval that you're finding the area under. Okay, the more concave it is, the worse the error. That's why that's there. It's directly related. The bigger the concavity, the greater the error. Okay? All right. Simpsons rule, I think I put in there, so you're good? Okay. Super wonderful lesson. Fundamental theorem of calculus. Okay. Now, you guys later in summer break, I'll summarize, sit around, I get up and I have my coffee and I just think about the fundamental theorem of calculus. Just spend hours just thinking about the fundamental theorem of calculus. That to me is super fun. Yes. And yes, I do have friends. Yes, I do have a wife. I did meet a girl, so take that. Harrod's rule. All right. So then, anywho, the fundamental theorem of calculus, I could think of this a million different ways, but this is my favorite. Yes, I have a favorite. So in the beginning, there were derivatives, and we could say that Newton and Leibniz got together, although they hated each other, and they said, here, let's put our two notations together. Do you agree that the derivative equals the derivative? Yeah, good. I'm so glad. I wouldn't know what to say if you said no. All right, so if the derivatives are equal, then we could split these differentials and get dy is f prime of x dx. Now think of that as a little rate times timing calculation, but it really means not a delta y, but more of a microscopic dy. So it's a tiny change in y. Now, if you then made many of these calculations, if you summed up many little changes in y, you would get a big change in y, or a total change in y. Total, would you put net in there? Change in y. You could say, I mean, if it's possible that it grew a lot and shrunk a lot, and you're right back to where you started, and so it might look like a zero, but it really did change, all right? In calculus symbols, though, if you were to sum many of these calculations, then that means sum many of these calculations, which is the integral. And if I were to say this is equivalent to the total change in y, isn't that the f value at the ending point take away the f value at the starting point? Isn't that the change? Well, that is the fundamental theorem of calculus. Integrating a rate of change gives you a sum of lots of little changes, which could be found by taking the antiderivative to actually get the thing you're talking about and finding the change. If you were to do this in a velocity case, is it dx dt equal to velocity? And if you separated those, is it dx a velocity for a microsecond times a microsecond? So think of it as a tiny rate times a rate at an instant times a little time gives us a little distance. So that's a little change of position, yeah? If I then integrated this, v dt, isn't that the sum of all those little rate times a microsecond, rate times a microsecond? And it doesn't matter that the rate's different because they're only using a microsecond. And so isn't that then total change in position? Okay, the antiderivative. Lots of little rate times time calculations. Blows my mind again, still does. All right, now, oops, darn it. That said, if you were to sum up all of integral calculus, You would say integrating a rate of change gives amount of change, not amount. It gives you amount of change. If you want amount, then you can't just consider change, you have to consider the initial, okay? So initial or start plus change gives you amount, so that might be something like f at 0 plus the change being from 0 to some point. What was the rate of change? Oops, I would need a dummy variable there. Let's use u like this. Okay? Gives you ending amount, or ending amount at any time. That's the fundamental theorem, just rearrange. It is more common, though, that instead of looking at this as the integral of f prime, they say, rather than look at this as the derivative of something, I'm just going to look at it as the function. And so, if you think of, I should have erased all these notes, sorry. If you think of the integrand as f, not f prime, then it's still the idea that you would have to find the antiderivative of that, which is capital F at the difference. Now, I know you've been doing this a million years, but just to remind you, to find a definite integral or evaluate a definite integral, what are the two things you do? You integrate or take the antiderivative, and then you plug and chug at the upper minus at the lower. Would it surprise you to hear that sometimes people forget to integrate? And they would actually say this integral from 0 to 2 of 2x plus 3 is 2 times 2 plus 3 minus 2 times 0. That, if you do that, I will come to your house on July 5th and I will beat you as hard as I can. Okay? Okay. Definite integral is area, positive, negative. If you look at this kind of deal, if you think of this as rectangles, then wouldn't you say that because f is positive, that the integral, which represents the area, should be positive? And if you had a region where the curve was below the axis here, it only stands to reason that because f is negative, the integral, or the sum of the areas, will be negative. Now, surely we want it to sometimes be negative. If you're talking movement, for example, it's important to know that it's negative. There are some problems where it says, find the area. Now, we'll do that tomorrow, but you need to distinguish, is this a case where I have to make it positive because they said find the area, or is it just, hey, here's the integral, go, okay? Sometimes positives are fine, and sometimes negatives are fine, okay? Just to remind you, the rectangle has two components. It's not just the function, it's also this guy. What if you went from 0 to 5, but your integral read from 5 to 0? If that's the case, then dx, or delta x, is negative, and your answer would be negative. Because of that, we typically switch the limits and negate, but when those limits go backwards, we negate it because that means delta x is a negative. All right? So just to check here, say I gave you this here function, this is f, and I told you this, positive or negative? It is positive because f is negative and dx is negative, and that's going to be a positive. Okay? Use geometry when possible. Obviously, if you get a semicircle or a line making a rectangle or a triangle, geometry is not only fine to use, but encouraged. It's easier. Okay? Obviously, it's crucial that you understand your graphs. If I give you this, let's go, I think that's an homework, I don't want to do that. If I give you this, there's definitely a hard way and an easy way to do that. The hard way is to say, okay, here I go, trig sum, blah-de-da-de-doo. Okay, what's the easy way?
Symmetry.
That's
That's a circle.
a circle. It's half of a circle, top half of the circle, geometry. All right. All right. Rules for definite integrals. We know we've already talked about the switchy switch. If you go from 2 to 0, that's the same as the opposite from 0 to 2 because the dx is negative. We talked yesterday about how splitting is okay. Additivity in terms of definite integrals. These are sometimes gotcha-ish questions. If you had 0 to 2 in a function and 2 to 4 in a function, is that equal to 0 to 4? Yeah, it is. It's no problem, okay? Additivity isn't a thing. Even odd is not a huge deal, but even has symmetry at the y-axis. That's supposed to be symmetric. So if you said negative 2 to 2, it's equivalent to double 0 to 2, right? If it was even. Odd has symmetry at the origin. And so if you said negative 2 to 2 in an odd function, it is 0. Area above and area below will knock each other out, right? Okay. Analyzing functions defined as an integral. Integral defined functions are area accumulation functions. Let's say I draw me a semicircle like that and a triangle like that. Make it isosceles, I guess. And I told you that this is f. An integral defined function could be something as easy as what's the area from, let's go 2 to x of f of t dt. These are very common questions. They are Calc 1-ish type of questions, and you could go a lot of different ways with this. This is the most common question in all of AP Calculus tests. It is, some form of this is almost on there every year. So I would usually hit this more, but you guys are really pretty good at this. I would start, just as a hint or a suggestion, if you get one of these points, I would start by writing the relationships. G prime is F and G double is F prime, and I would get that on my paper before I did any, because that right there probably just got me 2.7. I would still put it in my reasoning and all that stuff, but write it right away. This is the area accumulated from 2 to a point. Tell me this, G of 0, positive or negative? Negative, because the integral from 2 to 0 involves going backwards in a positive area, it is negative. And then you can have absolute min and max and all these different things, so but you guys are pretty good at that. All right. Darn it. Integral, right. Initial conditions, using them 2 different ways. Am I right? Is this the right place in your notes?
Yes, please.
Okay. So, here we go. There are 2 ways to use an initial condition. It's expected you are able to do both, no problem. One way is to use an indefinite integral and find the plus c. So you could say that f is the antiderivative of this. I beg you, please be aware that not always, when you put a 0 in, does it 0 out? You need to know to slow yourself down. Wouldn't you agree the antiderivative is 3 halves x squared plus 2e to the x plus c? If I put in the initial of 2, I get 0 plus 2e to the 0, which is not 0. So if you're one of those turkeys who just thinks, oh, f at 0 is 2, so that means c is 2, well, then you really don't know much calculus, because c is not 2, it is 0. Okay, if you actually take the time to put in 0 and see what happens, you see that c is actually 0. Do not rush to judgment. Do things the right way. It's not some homework you're trying to crank out so you can go on a date. It's your AP test. Do the work well. Okay? Another possibility is by definite integral. You could say f at some x is the starting plus the change. And I would probably use something like that. I could say the starting is 2, the integral from 0 to x of 3x plus 2e to the x. I could integrate 3 halves x squared plus 2e to the x from 0 to, this should be a u in here, or t, huh? Sorry about that. T, sorry about that. 2 plus, when I put an x in, I get 3 halves, this is a mess now, sorry. X squared plus 2e to the x. When I put 0 in, I get 3 halves of 0 plus 2e to the 0. 2e to the 0 causes that to go away. And again, I have the same function. Be adept at both. They're both skills worth knowing. All right. Boom. Okay. Fundamental theorem of calculus part 2. That is the idea that the derivative and the antiderivative are inverses. These sometimes are easy in that they ask you to just take the derivative, the antiderivative, you just have a nice x up there, and then you just put x into the function and call it good, right? Sometimes, however, you get a function up there, in which case you do more of a chain rule. You do put u in, but then you have to take the derivative of that. The y of that I've taught, but most people don't use the y, they just use a shortcut. Average value, I beg you, I think I've said it a lot today, but I'm begging you a lot. Average value versus average rate of change. Please read carefully. The word average is really loaded. It could be two totally different approaches depending on what they're looking at. So read carefully. Average value versus average rate of change. The average value is the idea of the 1 over b minus a kind of integral like this. They don't usually on the AP test throw you some crazy vocabulary test. Mean value theorem for integrals versus mean value theorem. But mean value theorem for integrals means there is a place, there is an x equals c where the average value is made. If I were to illustrate the two things, anytime they just say MVT with no qualifier, it's assumed to be the derivative version, okay? It is the idea that if I had a curve here, and maybe it looks like this, that if the average rate of change is the slope between those 2 points, there's got to be a place in here where the tangent slope is the same. The place where that happens is the C, guaranteed by the mean value theorem, period. If, however, they said, what about the C guaranteed by the mean value theorem for integrals? Totally different. Draw the same curve, so as to illustrate the point, but the mean value theorem for integrals says, first of all, find the average value. The average y value would be maybe in here somewhere where the area below and above kind of cancel out, right? That's f at c. The average value, the c guaranteed, though, is the x on the curve where that average value is made. And so you find the average value, but then trace it back and say, oh, the x at which it's made is 11. Okay? They're different. This is the average value. Okay. Moving on. Here we go. Never mind. Ignore those. Okay. Quickly, that first integral, what does it mean? Displacement or change of position. What if velocity is positive on the interval? It's also distance. If velocity is positive, also distance. Distance and displacement are working at the same time. What about the integral of speed? That's distance, sorry. What about the third one? Average velocity. It's the average value of whatever's in the integral, in this case velocity. Next one. Average speed. Last one, that's initial velocity plus, now this, think units, never forget to use units as a standby. Acceleration, say it was feet per second squared, time was seconds. Wouldn't that be feet per second. So it's initial velocity plus change in velocity. That's velocity at time t. Okay, this guy, average position. This guy, average acceleration. Integrate acceleration, you get position, velocity, neither. Change in velocity. Don't forget to once in a while you could actually say, well, fundamental theorem says antiderivative is v, subtracted. Doesn't that just slap you in the face with change in velocity? What about this? Initial position plus change is position at time. And the last one, this is a great gotcha. It's starting position plus distance, and that gives you nothing. If I said I started at 2 and went 70 units, what does that tell you? Nothing. I have no idea from forward, backward. It tells you nothing. Have a great day. I'm putting keys on mine. I'll eventually get caught up, but you really, if you have questions, you need to come and sit before school. I'm doing my best.
Yeah.
Yes. Yeah. Oh, food. Arnie. Hi. Yeah, it's fine. It's like that.
It's like graphically it looks positive, but
Yeah, so that's what I thought. I did it, I knew that wasn't right. So here's the deal. Absolute value didn't used to exist. Absolute value used to be this. This got replaced with absolute value, and that's really what's going on here. When they say x minus 1 quantity squared, that's really the same as the absolute value, so it's making it positive. Now, if I look at that, then that graph without the absolute value would be this, right? And so, really, that integral is equivalent to this. That's what's positive. That was a hard one. Hi.
can I just turn it in without the transformation?
Yeah, no, I have an answer for you. Okay, sounds good. Have a good day. What's that?
I said I'm not about that getting.
You're not about that?